In the last lecture, we saw that it is easy to solve the homogeneous system B x equal to theta m if B is in row reduced echelon form. This involved eliminating pivotal variables in terms of non-pivotal variables and choosing non-pivotal variables arbitrarily over f. And therefore, our job was, can we reduce a given f m by n matrix A to a row equivalent matrix B which is in RRE form. This would enable us then solve B x equal to theta m instead of A x equal to theta m. And since B x equal to theta m is easy to solve, being in row reduced echelon form, we would have solved the system A x equal to theta m. So, the main question was the reduction process. In the reduction process, we first introduce the first column operation. The first column operation was the following: given any matrix K in F P Q, you scan the first column, brought a non-zero entry to the top if there is one, and made it 1 and made everything below that 0, and if the first column had no non-zero entry, then we leave it alone. So, at the end of the first column operation, we get either in this form 1 0 0 0 and a submatrix K 1, which is obtained by eliminating the first row and the first column, or we get all zeros in the first column. In that case, we do nothing and we look at the submatrix we get by ignoring the first column. So, at the end of this, we get a matrix of the above type and we get K 1 having n minus 1 columns. Now, we shall go to the general reduction. The stage 1 is the following: you start with a given m by n matrix. A is an m by n matrix, and then you apply the first column operation on A, you get a submatrix A 1. This may be either of this form or this form. Let us call it as A 1. So, we get a submatrix A 1 which is of this form, and what we do is next apply the first column operation on A1, and then we get a submatrix A2 which has now 2 columns less than the original matrix. If we go on doing this, at the end of n minus 1 steps, if there are n columns, at the end of let us say n steps, at most we will get n steps, we will get a matrix which will be having its pivotal ones in the way we want. What do we mean by in the way we want? The pivotal ones will be the first non-zero entry in the non-zero rows, and they will be moving to the right as we go down to the rows, and all the entries below the pivotal ones will be 0. Okay. So, that is all non-zero rows will be above all 0 rows to pivotal entries one or in right place, we will just put right place, which means they are the first entries and they move to the right as we go down, and all entries below pivotal entries are 0. This is the first stage of the operation. This has got the pivotal entries in the right place, which has made the pivotal entries as 1, made them move to the right as we move down the rows, and made all the entries below the pivotal entries as 0. Now, the only thing that remains is the column supporting the pivotal entries must all be 0 except the pivotal entry. We have already made everything below the pivotal entry 0. You have to make everything above the pivotal entry 0. Again use elementary row operation. Stage 2, we will call it the cleanup operation. Make all entries above the pivotal entries 1 as 0 by using ERO of type 3, type 2. So, what we have done is, in the first stage we manipulated in such a manner that we got our pivotal ones, put them as the first entry in the non-zero rows, put all 0 rows at the bottom, and moved the pivotal ones to the right as we move down, made all the entries below the pivotal entries as 0. In the second stage, we flipped and made all the entries above the pivotal entries also 0. That cleans up and brings the matrix into this row reduced form. So, what we get in the end is called, end up with what is known as that final matrix is called the row reduced echelon form of A, and we denote it by AR, denoted by AR. So, we start with A, we go on doing first column operations, first on the first A1, then the A2 and the A3s and the A1s, and then subsequently when we get some matrix say A tilde, then we do the cleanup operation on this to get the row reduced echelon form. So, there are 2 stages in this reduction form of a given matrix to the row reduced echelon form. First, you adjust the pivotal ones and the entries below the pivotal ones, and then you adjust the entries above the pivotal ones in the cleanup operation. Let us look at a very simple example. Consider the matrix 1 2 2 9 minus 1, 1 2 3 3 13 minus 2 and so on. It has 4 rows and 5 columns. This is obviously not in row reduced echelon form, because take the first row which is a non-zero row. Yes, there is a first non-zero entry is 1, however, everything below that is not 0. So, we have to now apply our algorithm, our reduction process to this matrix to bring this matrix to the row reduced echelon form. So, let us do this process step by step. What do we do in the first step? The first step says take the matrix, scan the first column. The first column, does it have non-zero entries? Yes, there is a non-zero entry, there is a non-zero entry, all are non-zero entries in fact. We want to bring one of them to the top, there is one already in the top, that is the first stage, it is already done for us, and next stage is to make that first non-zero entry as 1, it is already 1. So, we do not have to do anything, and then we have to clean up everything below that non-zero entry. So, the first thing that we are forced to do here is now take this pivotal 1 and clean up in such a way that the entries 1 in the second row, minus 1 in the third row and 1 in the fourth row of the first column all get knocked off to 0. This we achieve by the following elementary row operation. To knock off this 1 in the second row, we have to subtract the first row from the second row. So, that we get a 1 minus 1 and this will become 0. Similarly, to knock off this minus 1 in the third row, we have to add the first row. So, that that 1 added to this minus 1 will give me a 0 here. Analogously, to eliminate this one, we have to subtract the first row from the fourth row to get a 0 here. So, the operations that we are looking for are R2 minus R1, R3 plus R1, R4 minus R1. And what do we get? We get 1, 2, 2, 9 minus 1. Now, this 1 minus 1 R2 minus R1 gives me 1 minus 1 0, 2 minus 2 0, 3 minus 2 1, 4 and minus 1. R3 plus R1 gives me 0, 0, 1, 4, 0. And then R4 minus R1 gives me 0, 0, minus 2, minus 8 and 3. So, this is the effect of doing the first column operation on the first column of the given matrix A. This completes full operation of the FCO on the first column of the matrix A, at the end of which we get the first column, a pivotal entry and everything below that 0. What we do next is we look at the submatrix obtained by eliminating or ignoring the first column and the first row. The submatrix that we are looking for is this submatrix consisting of 3 rows and 4 columns. Now, what we do is we apply the first column operation to the second, to this submatrix that we obtain. If we now look at this submatrix, the first column, it is all zeros. There is a 0 here, there is a 0 here, there is a 0. This 2 here does not count, because we are going to concentrate only on this submatrix. Now, all the elements in the first column are 0, and our algorithm said when the first column has all zeros, the FC algorithm says do not do anything. So, we just leave it as it is, then we look at the submatrix that we get by ignoring that first column of that submatrix. Then we get a newer submatrix which is now 3 rows and 3 columns. We now have to apply the first column operation to this submatrix. So, our focus is only on these 3 entries in the first column, because we are only focusing on this submatrix. So, now again if you look at this first column, there are non-zero entries and we have already a 1 at the top. Our main aim is to bring a 1 to the top and it is already there. So, now we have to do only a clean up thing, everything below that to be 0. To knock off this 1, we have to subtract this row from this row, and to knock off this minus 2, we have to 2 times this. So, now we will keep track the same number as the original row numbers. So, we have from the third row subtract the second row, from the fourth row add 2 times the second row, and what do we get? Nothing happens to what we got here and nothing happened to these zeros, nothing happened to these zeros. So, our operations do not affect what we have already obtained. Now, the real action takes place. From the third row we have to subtract the second row. So, the second row also remains as it is. From the third row if we subtract the second row, we get 0 0 1. Then from the fourth row you have to add 2 times the first second row, you get 0 0 1. So, this completes the first column operation on the submatrix that we were looking at the end of which therefore, we now look at the submatrix obtained by ignoring the first column and the first row of the submatrix. Now, this new submatrix, we scan the first column again, it has all zeros, and our algorithm says in a submatrix when you are looking at the first column all the entries are 0, do nothing. So, we just leave it and we look at the remaining submatrix that we have got. It is a 1 column matrix and we have all the entries non-zero, and we have to bring a 1 to the top, and we already have a 1 at the top. These are all the pivots. We already have the 1 at the top, and now we have to clean up, we have to finish up the 1 below that to be 0. To that we have to simply subtract the third row from the fourth row, then we get 1 2 2 9 minus 1 0 0 1 4 minus 1 0 0 0 0 1 0 0 0 0 0. These are the pivotal ones which have now been brought into position. Everything below the pivotal ones, all the entries below this pivotal one is 0, all the entries below this pivotal one is 0, all the entries below this pivotal one is 0. So, that completes the first stage of the reduction process. This applies only the first column operations. You go on applying the first column operations to one submatrix after the other, each time the size, the number of columns getting reduced, and finally you are left with one column. You apply the FCO to that, and then you are done with the first column operations. So, at the end of the first column operation, you will always end up with a matrix of this form. The 0 rows will be at the bottom, non-zero rows will be at the top. The first non-zero entry in each row will be 1, and as we move down, the non-zero pivotal ones will be moving to the right, and every entry below the pivotal ones will be 0. This is the end stage of applying the first column operations. Then we go to the cleanup operation. In the cleanup operation, we have now to choose one by one the pivotal entries and make all the entries above the pivotal entries as 0. So, now we already have chosen this one and made everything below this one as 0, and there is nothing above it. The next pivotal one is in the second row, and we want to make everything above it, namely this 2 this pivotal 1 above this is 2 and this 2 has to be now knocked off. To achieve this we have to subtract twice this to knock it off. So, we have to subtract twice the second row from the first row. So, that will be our next operation R 1 minus 2 R 2, that will give me 1 2 0 1 1 0 0 1 4 minus 1 0 0 0 0 1 0 0 0 0 0. Once again let me keep track of the pivotal ones. So, now we have made all the entries below this pivotal as 0 and there is nothing above it. We have made all the entries below this pivotal as 0, now we have made above also 0. Now, we go to the last pivotal one, we want to make everything above that as 0. To knock this 1, we have to subtract the third row from the first row. To knock this minus 1 off, we have to add the third row to the second row. So, we do these operations R 1 minus R 3, R 2 plus R 3, we get 1 2 0 1 0 0 0 1 4 0 0 0 0 1 and 0. This matrix in the end, now we have got after this cleanup operations, is in row reduced echelon form. Why is this in row reduced echelon form? We have non-zero rows on top and the 0 row at the bottom. Then if you look at the first non-zero row, the first non-zero entry is 1, then first non-zero entry is 1, first non-zero entry is 1. And as we move down, the pivotal ones are moving to the right. So, here is a pivotal 1, here is a pivotal 1, here is a pivotal 1, and as we move down, this pivotal comes down, then we move down, it goes to the right and so on. So, the pivotal ones are moving to the right and the column which supports a pivotal 1 other than the pivotal entry all are 0, other than the pivotal entry all are 0, other than the pivotal entry all are 0. So, therefore, this matrix is in row reduced echelon form. This is called the row reduced echelon form of A. Thus, our original matrix 3, which was a 4 by 5 matrix, which was not at all in row reduced echelon form, has now been brought by a sequence of elementary row operations into a row reduced echelon form. Therefore, instead of solving the original A x equal to theta m, the homogeneous system corresponding to the original matrix has same set of solutions as A r x equal to theta m. Now, let us recall how we solve this row reduced echelon form A r x equal to theta m. We first identify the pivotal variables. The pivotal variables are the variables corresponding to the columns in which the pivotal ones appear. So, there is a 1 appearing in the first column here. So, x 1 is a pivotal variable. There is a 1 appearing in the third column here. So, x 3 is a pivotal variable. Though it may come in the second row, it appears in third column and therefore, x 3 the column index tells you the pivotal variable. So, x 3 is the pivotal variable. The third pivotal variable appears in the fifth column. So, x 5 is the pivotal variable. You may recall we have seen this example earlier also. So, we have x 1, x 3, x 5 pivotal variables. and x 2, x 4 non-pivot. The remaining two variables are the non-pivotal variables. Now, what is the homogeneous system ARX equal to theta m? If you look at the matrix, the first equation is x 1 plus 2 x 2 plus x 4 equal to 0. The second equation is corresponding to the second row, no x 1, no x 2, x 3 plus 4 x 4 is equal to 0. So, it is x 3 plus 4 x 4 equal to 0, and the last equation similarly is x 5 equal to 0. Again the pivotal variables of x 1, x 3 and x 1. And what we do is the first equation eliminates the pivotal variable x 1, and when you eliminate the pivotal variable x 1, we get only in terms of x 2 and x 4, and the other pivotal variables do not occur. Similarly, when you eliminate from the second equation the pivotal variable x 3, it is only in terms of x 4 and not the other pivotal variables. The last equation eliminates the pivotal variable x 5 and it does not involve the remaining two pivotal variables. So, therefore, we eliminate the pivotal variable x 1 as minus 2 x 2 minus x 4, the pivotal variable x 3 as minus x 4 and the pivotal variable x 5 as 0. And the non-pivotal variables x 2 and x 4 can be chosen arbitrarily. So, what is the general solution then? Any solution x is of the form x equal to, remember x 2 has to be chosen as minus, x 1 has to be chosen as minus 2 x 2 minus x 4, x 2 can be chosen arbitrarily, x 3 has to be chosen as minus 4 x 4, x 4 can be chosen arbitrarily and x 5 must be chosen. So, we will denote the two arbitrary fellows, the non-pivotal variable x 2 as alpha and x 4 as beta, then x equal to minus 2 alpha minus beta, alpha minus 4 beta, beta and 0, alpha beta chosen arbitrarily in F. Or we can separate the alpha and the beta, the two degrees of freedom we have, we can write it as minus 2 1 0 0 0 plus beta into minus 1 0 minus 4 1 0 alpha beta belonging to F. Now, by varying alpha and beta over F, we get all the solutions. Get all the solutions of the homogeneous system ARX equal to theta m, and since ARX equal to theta m has the same solutions as AX equal to theta m, we get also and hence all the solutions of AX equal to theta. Now, therefore, the general strategy for homogeneous system turns out to be the following. A is given, you look at A x equal to theta m is the corresponding homogeneous system. Look at A, you apply the first column operations, get a matrix A tilde, then you do the cleanup operations which we had described, and you get the row reduced echelon form. Solve A r x equal to theta m by eliminating pivotal variables in terms of non-pivotal variables and choosing non-pivotal variables arbitrarily. You have to choose the non-pivotal variables arbitrarily. You have all the freedom over f. And that is the general strategy. If we solve, and the same will be these will also represent all solutions of the original system we started with A x equal to theta. So, the solution of a homogeneous system corresponding to a matrix A can be systematically handled in two stages. One, by using the first column operations and the cleanup operations to reduce the given matrix to the row reduced echelon form, and then instead of solving A x equal to theta m, solve the easier system A r x equal to theta m. It is easier because it is in row reduced echelon form. And once you solve A r x equal to theta m, there will also be the solutions of A x equal to theta m, because both A and A r are row equivalent. Now, let us make some remarks. Let us look at a general matrix A which is m by n, and when we reduce A to the row reduced echelon form of A, row reduced echelon form of A by our usual first column operations and cleanup operations. So, you apply first column operations and the cleanup operations as described above, you get the row reduced echelon matrix. Now, once you look at A r, it has a row reduced echelon form, therefore, it has certain non-zero rows followed by a certain number of 0 rows. There may not be any 0 rows or there may not be any non-zero rows, but in general there will be certain number of non-zero rows sitting at top and all the 0 rows would have settled down at the bottom. Now, suppose say A has m rows, some of them are non-zero and some of them are 0. Let us say there are row number of non-zero rows. So, let A r have row non-zero rows. Therefore, it has m minus row 0 rows, because the total number of rows is m, a row of them are non-zero. So, the remaining must be 0. So, A r will be of this form. There will be this row 1, there will be this row 2, there will be this row r row, let us call the row 1 as r 1, row 2 as r 2, row as r row, and then the r row plus 1, the row plus 1th row will all be 0, and it goes down and the mth row will be all 0. So, there will be m minus rows which are all zeros which are now settled down at the bottom, and at the top we will have row non-zero rows. Now, let us look at the first row. It will have a first non-zero entry, and we had the notation, let us assume that the first non-zero entry of R 1 appears in K 1 column, R 2 appears in K 2 column, and R row appears in K row column. So, let the first non-zero entry, which we called as the pivotal entry of row R I, appear in K ith column, appear in K ith column. So, the matrix will now look like AR, there is this zeros, the R row plus 1 down all the way to R m, all these are zeros. Now, in the first row, in the K 1th column there is 1, all the others are 0, and since everything below and above a pivotal one must be 0, it will all be like this. And then in row 2 there will be a column K 2 to the right, and 1 will appear there, and all others will be 0, and it will go on like this up to K row. So, therefore, we have the non-zero entries in the Rith row appearing in the Kith column. Now, we know that the variables corresponding to the pivotal ones are the pivotal variables. So, the pivotal variables will be xk1, xk2 and xk row. The non-pivotal variables will be xj, j not equal to k1, k2, k row. Okay. These are eliminated in terms of the non-pivotal variables, and these are chosen arbitrarily. Now, the number of pivotal variables is equal to rho, which is the number of non-zero rows in AR. The number of non-zero rows in the row reduced echelon form of the matrix is the same as the number of pivotal variables, and that is denoted by rho, and this number is called the row rank of the matrix A, called row rank of the matrix A. So, what is the row rank of the matrix A? So, the definition is the row rank of A is the number of, it is a number, it is a whole integer, the number of non-zero rows in the RRE form AR of E. Let us look at an example. In our example, we saw we reduced a matrix to this following row reduced echelon form. if you look at this matrix, this is already in row reduced echelon form. So, we do not have to do any reductions. So, that itself is its row reduction reduced echelon form. How many non-zero rows are there? There are precisely 3 non-zero rows. So, row rank of A is equal to 3. Consider this matrix which is the 0 matrix, 2 rows and 3 columns. Is it in row reduced echelon form? Yes, because what is the structure? All 0 rows must settle down, and if there are non-zero rows, they must come on top. There are no non-zero rows, all are 0 rows. So, the row rank, which is the number of non-zero rows, in this case is 0. So, the row rank of A is equal to the number of non-zero rows, which is also equal to the number of pivotal variables, number of pivotal variables. Now, if there are row pivotal variables, how many non-pivotal variables are there? So, the total number of variables or unknowns or whatever we want to call them, there were if it is an m by n matrix, the unknowns are x 1, x 2, x 3, x n. So, the total number of variables is n, number of pivotal variables is equal to rho, which is the row rank of the matrix. Therefore, the number of non-pivotal variables is equal to n minus rho. There were n rows, n pivotal variables in all, row of them were pivotal. So, n minus rho will be non-pivotal. This is called the nullity of the matrix A, called the nullity of the matrix A. So, the nullity of the matrix A is equal to n minus rho, or we have rho is the row rank. So, row rank of A plus nullity of A is equal to the number of columns in A. This is a very useful result which will be seen in different forms later, but this is the same thing as saying certain number of variables are pivotal, certain number of variables are non-pivotal. Looked at from the homogeneous system of equations point of view, we talk the variables language. So, the number of pivotal variables plus the number of non-pivotal variables is equal to the total number of variables. Purely from the matrix point of view, we say that the row rank of the matrix A plus the nullity of the matrix A is equal to the total number of columns in the matrix A. So, so far let us summarize. We know or we have learnt, so far we have learnt that how to solve homogeneous systems, how to solve homogeneous systems. The idea we have seen, reduce the given homogeneous system by reducing the corresponding matrix to the corresponding row reduced form and solve the row reduced echelon form equation and thereby get the solutions. So, we have a clean picture, a clean method or a clean algorithm to handle homogeneous systems. If you recall that when we solved non-homogeneous systems, the solutions of non-homogeneous system we said involved two parts. One was finding the solutions of the homogeneous system, which we are now clearly handled by reduction to row reduced echelon form. And we also had to find a particular solution of the non-homogeneous system to put together a complete picture of the solution of the non-homogeneous system. So, now let us proceed towards handling NHS, the non-homogeneous system. It remains to find a particular solution XP of the non-homogeneous system, because we said that any solution of the non-homogeneous system can be obtained as XP, which is a particular solution, by adding to it a solution of the homogeneous system. And since we already have all the homogeneous solutions system, we have seen how to get them. All we need to find is one particular solution of the non-homogeneous system. Now, how do we go about doing this? We shall look at the first idea towards this. Now, why does not the same thing that we did for homogeneous system work in this situation also? So, for that we shall see what was the strategy for homogeneous system. We used UROs. Basic idea was used UROs. Now, the UROs were the ones that were used to reduce the given matrix to the row reduced echelon form. Now, what exactly is the effect of EROs that we are doing on the matrix A when it comes to this homogeneous system corresponding to them? When we are doing some operations on the rows of a matrix, which means that we are trying to do the same type of operation on the corresponding equation left hand side. For example, if we had a matrix A and this is the ith row, and if we had performed an ERO on Ri, so we are going to perform an ERO on Ri, then it boils down, like for example, to this ith row I add some multiple of jth row, or I multiply the ith row by a constant. In terms of the system of equation, what we are doing is we are looking at the ith equation equal to 0, and we are doing the same operation on the left hand side. In other words, we are multiplying this row, that means we are multiplying the left hand side of this equation by alpha. If we are adding 4 times the second row to this equation, it means we are adding 4 times the second equation left hand side to this ith equation. Similarly, if we are interchanging 2 rows, here it means we are interchanging the 2 left hand sides of this equation. So, EROs on matrix A is same as the, from the point of view of homogeneous system, similar operation on the LHS of corresponding homogeneous system. Now, an equation has both left hand side and the right hand side. If you want to do something on the left hand side to maintain the equality, we must do the same thing on the right hand side. Why are we not doing it on the right hand side? The reason is the right hand sides are all 0 in a homogeneous system, and therefore, if you do any of these elementary row operations, the right hand sides are not going to be affected, they remain to be zeros. So, we notice that none of these EROs affect the RHS, because they are all 0, and they remain to be 0 after the ER goes, and therefore, we do not even bother to do these EROs on the right hand side, and hence the system becomes, and therefore, this implies AX equal to theta m and ARX equal to theta m will have same solutions, because both the right hand sides are going to be still theta m only. Why does this not work in non-homogeneous system? This will not work in NHS. What do we mean? What we mean is, suppose I go from A to AR by elementary row operations, and I add a B in FM, then I look at AX equal to B and ARX equal to B, the two non-homogeneous system, they need not be same solutions. The both need not be having the same solutions. Now, previously when we retained the same right hand sides, when we had homogeneous system, we retained the same right hand sides both sides, but now if we try to retain the same right hand sides, the systems are not going to be equivalent, because let us the right hand sides will change. Let us look at an example to illustrate this. Let us consider the matrix A equal to 2, 3, minus 1, 1, minus 1, 1, and B equal to 2, 1. Now, if you look at this matrix and do the following row operation, there are only 2 rows. So, let us interchange the first and the second row, 1 minus 1 1, 2 3 minus 1 1. Now, this is, let us call it as A1. So, I have a system generated by this matrix A, and I have now made a elementary row operation on this matrix. Now, look at the non-homogeneous systems AX equal to B and A1x equal to B. These are the systems. A is 2x1 plus 3x2 minus x3 equal to 2, and x1 minus x2 plus x3 is equal to 1, and this is the system x1 minus x2 plus x3 is equal to 2, x1 minus 2x1 plus 3x2 minus x1 equal to 1. Notice that both these systems are different and they will not have the same solutions. We will leave it as an exercise for you to find one solution which is a solution of Ax equal to B and which is not a solution of A1x equal to B. Therefore, elementary row operations affect the solutions if we do not change the right hand side. How do we handle this? We shall see that in the next class.